Okay.
Okay, so let me know, please let me know where I should start.
Yeah. So I think we can start. Welcome back to the Thursday session of the school. Uh, we will have now the second lecture from Dominik Kwietniak. So Dominik, take it away.
Okay, thank you very much. Let me start with a quick recapitulation of what I have said last time. So our main problem for a moment was the classification of subshifts with respect to the conjugacy relation, which is defined here. So it turns out that the conjugacy relation for subshifts is an example of a so-called countable-Borel equivalence relation, meaning that the set of pairs of subshifts which are conjugate are elements is a subset of some Polish metrics, Polish space, and therefore we can talk about this equivalence relation being Borel. Moreover, by the properties of subshifts, we know that all equivalence classes are countable. So this puts the problem of conjugacy of subshifts into a framework studied in descriptive complexity of equivalence relations. And in that framework, we uh, compare two equivalence relations by by the notion of Borel using the notion of Borel reducibility. So we say that one equivalence relation on one Polish space is Borel reducible if there is a function Borel map uh, which has this special property uh, that here you can see it that for every 2 points in the first space, they are in the first relation, even only if their images are in the second relation. So this, if this holds between two equivalence relations of Polish spaces, it is fair to say that the first relation is at most as complicated to classify according to that relation as the second one, because if we have a way to resolving the question whether two elements of the second space are in the second relation, then we can use this Borel reduction to get the answer for the first space as well. So, so then we said that the ideal resolution to a problem of classification is to find a reduction to equality on reals, because finding such reduction is a finding a complete set of invariants which are moreover Borel computable. So there are some examples of that, and but not unfortunately not all not all countable Borel equivalence relations allow for such invariants. Then we concentrated for a moment on the picture of classes of countable Borel equivalence relations with respect to this partial order given by Borel reducibility. And let me redraw this picture because this is important. So we have the lowest point of this picture are smooth relations. So relations be reducible with, okay, again, as the last time, we consider only relations with uncountably many distinct equivalence classes. I don't for a moment we ignore those simpler ones with too few classes to be interesting from our point of view today. So they are first the lowest point, the simplest in the Borel order are smooth relations. So those are relations which are Borel equivalent, be reducible to the identity relation on reals. Then the next complexity class are hyperfinite relations. So those are which are Euler reducible to the relation E0. I should call it maybe eventual equality on 0, 1 to infinity. So this is the next, and next we have the whole big world of uncountably many distinct classes of complexity for equivalence relations, but we have one maximal one, which is actually the equivalence relation given by the action of, so this is the orbit equivalence relation on given by the action. So the notation was like this, like orbit equivalence given by the action of the free group with two elements on all functions from f2 to 0, 1. So you can think of it as a function of the free group generated by two elements on the set of all subsets of the free group. So those relations, so those are relations which are Borel be reducible with that, and that's the maximal element for countable Borel equivalence relation complexity. So that was the picture, and now uh, the first uh, part of today's lecture will be devoted to a possible answer to the following question. So we know also that Clemens proved that the topological conjugacy of subshift is of this maximal complexity among all Borel equivalence relations. Uh, so, so we now it is fair to say which subclasses of subshifts exhibit a similar uh, complexity, because it is to be expected that there are maybe some dynamically interesting classes of subshifts which show the same uh, complexity as the space of all subshifts. Or maybe not. Each answer would be interesting here. So we concentrate on the space of subshifts called subshifts with specification. So we call that every subshift over final alphabet uh, is determined and determines uniquely a set of words which appear in points in the subshift, so the so-called language of the subshift. And using using properties of the language, we can characterize certain subclasses of subshifts. So subshift is transitive if for every two words which you can see appearing somewhere in the subshift, you can find them together appearing in the given order in some single sequence in the subshift. So every two words appearing in the language can be joined by possibly empty third word W such that UWV appears in the language. If we can do the same, but having the word W of one and the same length, K for each pair of words U and V, then we say that the subshift has specification. So examples of the subshifts with specification are really all the full shift. Uh, and I provided one more example, which is the golden mean shift, which is the subshift defined by saying that a point belongs to the subshift if it is a binary B-infinite sequence in which no two ones appears next to each other. So that's the definition of the golden mean shift. And let me go back. That the golden mean shift xg has specification because if you are given any towards u v in the golden mean shift, then the word u 0 v in the language of the golden mean shift, then u0v belongs to the language of the golden mean shift. So uh, being in the language on the golden mean shift is an easy condition because a finite binary word is in the language of the golden mean shift even if 1 does not appear in u. So if I take two words in which 1 does not appear, and I put a symbol 0 between them, then gluing them all together, I get another word in which no two ones appear next to each other. So for sure, that's a word in the language of the golden mean shift. And this proves that my golden mean shift has the specification property. So, so in the word of there is a picture. I'm sorry, I don't have much time to explain uh, all the notions appearing here. I hope that in the audience we have some people knowing a little bit more about symbolic dynamics. This picture won't be important to what I am going to say, but for the information of the already informed people, we have that all mixing shifts of finite type have specifications. So golden mean shift was only one of the examples of many shifts of this type which have specification. Then this class is properly contained in mixing suffix shifts, and this class is and those systems uh, still those are subshifts with specification. And there are other examples. So there's a famous family of beta shifts. So beta shifts are codings of beta expansions. So expansions in base beta, where beta is not necessarily an integer. So among beta shifts, we have all possible type of examples. So all beta shifts are mixings. So among all beta shifts, we have mixing shifts of finite type. We have mixing examples of beta shifts, which are mixing suffix shifts, but they are not shifts of finite type. They are also beta shifts which have specification, but don't are not mixing suffix shifts. And they are beta shifts which are just mixing shifts which do not have the specification property. So this family of shifts with specification is important, uh, but it is like the first uh, non-trivial family with uh, enough examples to ask a question about Borel complexity of the topological conjugacy relation because the family of mixing suffix shifts and therefore also the family of mixing shifts of finite type, they consist only of countably many subshifts. So the topological conjugacy relation does not have uncountably many distinct conjugacy classes for those shifts. This conjugacy relation on those subshifts should be studied using different tools. Here, let me maybe state the main theorem, which partially answers Bowen problem about classification of shifts of finite type. So this is this problem 32. Classify shift spaces with specification. Unfortunately, Bowen didn't leave any hints what kind of classification he would like to see. So together with Konrad Decker, Bo Peng, and Marcin Sabok, we have the following partial answer to the question of Bowen. Topological conjugacy of subshifts with the specification property is not treeable. In particular, is not smooth, so no complete Borel invariance with values in a Polish space exist. So we have this no treeability result, which gives us the lower bound for the complexity. Let me go back because treeability appeared here. On the picture, it was it was defined here that an equivalence relation on the Polish space is treeable if there exists a Borel forest such that the equivalence classes are traced in that forest. So treeability is above being hyperfinite. So not treeable relations cannot be hyperfinite. Nor amenable. So let me now define amenable relations. So there are many ways of defining amenable groups. So let me recall that second countable locally compact Polish, okay, so locally compact Polish group, Polish topological group is amenable if and only if, so this is maybe not the definition, but not the most convenient definition, but one of the many one of the many equivalent conditions. So a locally compact Polish group G is amenable even only if it satisfies the so-called Reiter condition. And the writer condition says that there exists a sequence Fn of Borel functions. Each of n goes from G to the reals, such that each of them is a non-negative uh, function, has L1 L1 norm with respect to the Haar measure uh, on the group G1, and for every G in G, we have the following: the L1 norm of Fn minus the image of the natural action of G of on Fn in the norm 1 goes to 0 as n goes to infinity, where Gfn of is a function from G to R given by for H in G by Gfn of H is Fn of G inverse H. So that's one of the equivalent definitions of amenability for a group, and we can translate that definition to a countable Borel equivalence relation. A countable Borel equivalence relation is amenable if there exists a sequence Fn of Borel functions with real values which are non-negative, and if such that we have writing Fn of x of y equal Fn xy for any pair xy in E. We have that for every x, the fxn is an element of the space L small L1 of the equivalence class of E of x, and the norm Fn x1 is 1. And finally, if x and E are in the same relation, then we have that Fnx minus Fny, the L1 norm of this goes to 0. So that's a condition for an to defining amenable Borel equivalence relation, and we have the following family of examples of countable Borel equivalence relations. So amenable countable Borel equivalence relation. So every orbit equivalence relation determined by a Borel action of a countable, amenable group on a standard Polish space, standard Borel space, I'm sorry. Is amenable. So, in particular, it is also known that all hyperfinite Borel equivalence relations are given by actions of amenable groups, are Borel B-reducible with those. So, in particular, every hyperfinite countable Borel equivalence relation is amenable. And then there is a big open problem in the theory of countable Borel equivalence relation, which is the converse true, meaning that we don't know if every orbit equivalence relation given by a countable amenable group on a standard Polish space is hyperfinite. Neither we know, and so this is a concrete question, a more specific question, and more general question would be: is every amenable countable Borel equivalence relation hyperfinite? Let me do this remark, which I forgot to mention last time. I think that every countable Borel equivalence relation is given by a Borel action of a countable group on a standard Polish space. Standard Borel space, I'm sorry. Every uncountable Polish space without isolated points is an example of a standard Borel space. So we can think of that in this way. So what does it mean? It means that our result with Konrad, Bo, and Marcin puts the classification problem for shift spaces with specification, well, above this blue dotted line on the picture, in a sense, or outside this blue bulb. So we have this now. This is what our result says, and conjecture, which we were unable to resolve. At some moment, I thought I have a proof, but I was wrong. So conjecture says the following: the topological conjugacy of shifts with specification is the universal Borel equivalence relation. So it's this Borel be reducible with the orbit equivalence relation given by the free group generated by two elements action on the full shift over that free group. So this is what we expect to hold true, but right now that's an open problem. So now there's a question: how one proves such a property that something is not treeable, that some Borel equivalence relation is not treeable, and here we have the criterion, which is the following, that if we can find we know that every sub-equivalence relation of a treeable relation is still, well, any restriction of an equivalence relation to which is treeable to a subset is still a treeable equivalence relation. So what once so this tells us that the first reduction of the proof is that find a subfamily of shifts with specification, some subfamily B consisting of shifts with specification, such that conjugacy has uncountably many equivalence classes in B. That's one demand. Second demand is that conjugacy on B is not treeable. So that's the first step in the proof, to realize that you can do that. The second step, which I will not go into details because it's a fairly standard trick used in symbolic dynamics very often, is that if you can do it for some alphabet A with at least two elements, then the same holds for any alphabet A prime with at least two elements. So in particular, for the alphabet which is just binary. So one can be worried that if we say need a lot of elements in the alphabet, this causes the complexity to be high. But actually, this is not true. This is a technical recoding, uh, some kind of a recoding technique which allows um, you to translate this complexity between alphabets of different cardinality. So, so we have those two steps are now uh, easy, and I hope believable. Although the second step is a bit technical, uh, but let's go to the main idea of the construction. And again, I will just show you because that's simpler, but the idea is exactly the same, that you can get it using the we will just concentrate on showing that this relation is not amenable. So what we do? So first, take an alphabet, a tilde with at least 4 elements. Okay, it's like I don't care if maybe it has more than 4, but I need at least 4. Then I create the proper alphabet, which needs to have at least 5 elements, because I use a special symbol hash, which is an additional symbol. This, of course, a tilde is finite, but it needs to have at least 4 elements. Now I define the set A. Now I define the set of odd words. So this is all. This is the family of all W, which are finite words, over a tilde, such that the length of W is an odd number. So the next step is to define the following family of forbidden. So next is fix R, which is a family of odd words. And simply say that F of R consists of all words with the special form hash W hash for W in the set R. So this is those steps are performed in order to define XR, which is a subshift over A to the Z, and XR consists of all X in A to the Z, such that no word from FR appears in X. So in this way, we get a construction of, so what it gives us that over special alphabet with at least 5 elements, we have constructed a family of subshifts in which each subshift is defined using words with that family. So in particular, special words from FR does not appear. So let us look at those subshifts XR. So XR, they have this structure that let us observe that the full subshift over A tilde is always uh, in XR for every R. For every subset, this full subshift is in the shift XR because our conditions put no restrictions on words in which hash does not appear. So every combination of letters other than hash is allowed to appear. So every sequence in which hash does not appear is allowed. So moreover, uh, if I see hash somewhere in my sequence, then uh, if before I see another hash, I can put between those two guys any even number of symbols other than hash. So this space I can fill with elements of A tilde. So A tilde is the alphabet without hash. I can put here whatever. But if I see hash and then some empty space and another hash, and I assume that those two hashes are the closest to each other appearance of the symbol hash, and the number of positions between those two hashes is odd, that then I can put here only words out which are outside R. So only words outside R can provide an odd length gap, fill odd length gap between the appearance of two hashes. So this is the description of the shift space we get, and now it's good to prove something during a mathematical lecture. So let us do a proof that for every R, the shift space XR has specification. So take any pair of words in the language of XR. And then the important part is that I have to look at the last appearance of hash in U, and I have to also look into the first appearance of hash in V. Possibly there is no hash either in U or in V, but this simplifies the situation. So we have even if a simpler answer is like that if there is no hash in U or in V, then I can always put a hash in front of U and hash in front at the end of V, and proceed with my reasoning further. So now observe the following, that I have 4 cases to consider. So now I have this U, this is something something, maybe empty, something something, and I have V, which is something something hash something something. And now assume that those two guys are odd. One of them is even, or two of those lengths are even. There are four cases to consider. And in the first case, I need to take the element A twice to have like all together, then this will be, in the red case, it will be even number of elements, and even number elements between two hashes are always allowed. So this will produce an allowed word. So yeah, I'm sorry, my claim is that K, the length for specification, needed for specification is 2. So let us see that I can glue any two words U and V using 2 symbols. And indeed, if this remainder lengths at the end of U and the remainder length at the beginning of V before I see the first hash are odd, then I can put 2 symbols other than hash to glue them. And if I see even number of words and odd number of words, then I put hash A or A hash here. And if I see two even numbers of symbols, I'm sorry, then I put 2 hashes to glue those 2 words. So this proves that whatever I do, I always have the specification property for XR. So I can always do this stuff. So let me also notice that actually I can identify subshifts in XR with subsets of the countable set of all odd words. So I have this countable set. So let us notice that this set is countable. So now I can consider R to be element of the identifying R with its characteristic function. I can see that actually there's one-to-one correspondence between elements, those subsets and subshifts, because if I take 2 different subsets, then there is a word of odd length which appears in one of those subsets that does not appear in the another, and there will be a sequence which appears in one of those subshifts and does not appear in the other. So that's the actually bijection between those. I'm sorry, I need some more pages. Let me add some pages.
Dominik,
Yes.
is it maybe a good time to take a break?
Oh yeah. Oh sure. So let's make a break.
Yeah, so let's resume maybe at 10 sharp. Okay, let's resume at 10 sharp.
Okay.
Okay, perfect.
Okay, so now what is happening is that yeah. So we have defined a family of shift spaces with the specification property, and we know that it is enough to show that the topological conjugacy relation on this subfamily is not treeable or not amenable or not hyperfinite or not smooth in order to show that the whole topological conjugacy relation on all subshifts with specification is uh, not does not have the respective property. So how we do that is that using this identification we can think about our family as having a structure of the Cantor set, because we translate every subset of some countable set, we turned every subset of some countable set into some subshift with the specification. And the family of all subsets of a countable set has a natural topology of a compact Cantor space, because we simply consider this as the product of discrete space 0, 1 indexed by the elements of my countable set. So uh, so now there are some criteria for non amenability or non triability. So if we can now find a free uh, measure preserving conjugacy preserving action of now f2 times f2 free group with two elements on the family. Let us call this family curly R, or f2R, then topological conjugacy is not treeable, then topological conjugacy is not amenable. So the next step is to using again a piece of a theory of countable Borel equivalence relation to say that we need to now find an action which preserves some measure, and it is free, meaning that the set of points whose orbit with respect to the action are free has the full measure, and it preserves the conjugacy, meaning that each orbit of the action is contained in the one equivalence class of the conjugacy. Then if our acting group is free group times free group, then we can say that the topological conjugacy is not treeable. And if it is just the free group, then the topological conjugacy is not amenable. So this is how we deal with those problems. And now to give you a glimpse into those techniques, I will actually prove something even simpler. But I hope that this proof gives you some insight into the methods used for proving those other actions. So there's also a theorem which shows how you prove proposition, which goes back. Okay, maybe first definition. Let E be a countable Borel equivalence relation on a Polish space X. So X0 in X is a condensed point of E if X0 belongs to the set of accumulation points of its own equivalence class. So we look at all points which are in the same equivalence class as X0, but they are different than X0. If X0 belongs to this closure, so if X0 belongs to the closure of this, then we say that it is condensed point. And then we have a proposition due to Calderonian clay. Well, you can find the proof in Calderonian clay or in Osin. Maybe that this proposition was known among specialists even earlier, but those are two references where you can find this a proof. If gamma is a countable group acting continuously on a Polish space X, then if the orbit equivalence relation generated by this action of gamma has a condensed point, then this orbit equivalence relation is not smooth. So this is a criterion for not smoothness, and recall that non-smoothness is enough to say that the equivalence problem for the conjugacy problem for the substitute specification is already intractable for any reasonable Borel invariance. So now I will show that the topological conjugacy relation on this family XR given by the action of a countable group of automorphisms is really it has a condensed point, and this will prove that this relation is not so remember that what is the group of automorphism of the full shift is the family of all homeomorphisms such that they commute with the shift action. So now inside this group, I will consider a special subgroup which has good properties with respect to my family R. So remember that R consists of special subshifts. Of this form. And for those subshifts, I will consider special automorphisms. So I will write I will now define the special automorphism. So my phi will belong to the automorphisms of A to the Z, which preserves symbol hash. And an automorphism belongs to this subgroup if there exists phi star, a map on the space of all odd words, which is length preserving, which means that the length of the word W is the same as the length of the word phi star of W, and such that if I look at the image of the cylinder, so I look at the set of all points which have starting at the 0 coordinates the following sequence of symbols. I see hash, I see W, and I see hash again. So the image of the cylinder through my automorphism phi can be determined as the cylinder of hash, phi star of W, and hash. In other words, automorphisms in my special subgroup of automorphisms, they act like this, that in order for them to act non-trivially, what I'm interested in is how they act on sequences containing hashes. So the point is that my requirement is the following, that whenever I see two hashes at the odd distance next to another, then how my automorphism acts on those points depends only on what word I see between those two hashes, and then this word is substituted by the word given by phi star. And of course, this means that we have a subgroup of we actually obtain a subgroup of the set of all automorphisms in this way, and this subgroup also acts on my Carly R space in the following way, that if now imagine that I have I can extend my phi star to a transformation acting on the characteristic function of the subsets of R. So given R contained in the space of all odd words, given phi star which is of this type, I can now take the characteristic function of R, which is an element of 2 to the space of all odd words. And now I can act on this characteristic function by phi star. So to compute the image of this characteristic function, it should again determine a subset of the set of all words. Then I look at one of those all words, odd length words, and then I compute this in the following way. Of course, I assume here, I'm sorry, I should say that this is a bijection. So here, I will just look at the image of the characteristic function of R at the point phi star inverse of W. So this tells me that actually the any element of my group of hash preserving automorphisms also acts on the space of R of all subshifts with the family of my subshifts with the specification. So we see that we are really moving around this space. So this family of automorphisms is then used to prove those things, those two things, but I will use them to prove actually that there is the condensed point in the family of in R for the topological conjugacy, and this is enough just to show that this family is not smooth, because the proving that this action preserves some measure requires more work. So it will be easier to just show you a special case. So now the proof is, the proof just requires a hat just to contain two elements. I don't need any more than A, B, and this. Then of course A contains at least three elements. But again, the trick with recoding allows me to claim the same for the alphabet with any cardinality. Okay, so we are now in that situation, and I take R0. So R0 is the set of all words of odd length which consists only of the symbol A. So R0 forbids only one transition between two hashes. So only those words are forbidden to appear in X0 equal XR0. So now I will now I need to show that my x0 is a condensed point. So what I need to find is I need to find a sequence of subshifts which are contained in the topological conjugacy class of x0 minus x0 itself, such that my subshifts converge to x0 in the topology on the space of subshifts. So topology on the space of subshifts is like that two subshifts are close to each other, even only if their languages up to certain length coincide. So when k grows, I need to find that the language of xk differs from the language of x0 only for very long words. And how how it goes is that I know, in fact, that I so I will now find the word phi star k, which will have this one and only one property, that a word a 2n plus 1 will be a 2n minus 1, I'm sorry. Or maybe should be exchanged into word a n minus 1, b a n minus 1. So the word which consists of an odd number of ones should be turned k, not n, k here, I'm sorry. Should be turned into a word in which b appears. So such a transformation, when it is extended to the transformation on the whole shift, will exchange any occurrence of a2k minus 1 into occurrence of ak minus 1b, ak minus 1. And now I need to find actually an automorphism of my space, which is hash preserving, for which the determining length preserving transformation on the words of odd length will be my phase star of k. And this is easy. This is easy because I need to define phi k. And remember that what we need is a block map, which I mentioned at the first lecture. And this block map will be defined on the all set of all words of length 2k plus 1. And so what this block map does is looks into k minus words forward, looks at the position 0, and looks into k minus 1 symbols afterwards. And if this is the window, it maps it to just one symbol. I should be k minus 1. So it looks into one single symbol here. So how it goes? This block map is defined as follows: phi k on the word V0, V1, V2k minus 1 is equal. I'm sorry, here I should put 2. It should be really like this. Maybe I can simplify, but okay. This I don't want to go into the details, but it is like I look into the word and what I should see. If I see hash a to ak minus 1, and here I see ak minus 1 hash, then here I should really, what I should do, I should exchange any occurrence of A with any occurrence of B. And if in the window before or if in the window after I don't see this particular symbol, then I should do nothing. So this is Vn, this is A if V is equal hash A k minus 1 B A k minus 1 hash. This is B if V is equal hash A 2k minus 1 hash, and Vn otherwise. So with those definitions, I have a block map. Therefore, I have an automorphism of the shift, and this automorphism of the shift belongs to the space of to the subgroup of automorphisms which preserve hash symbol. And the action of this automorphism of my XR sequence that if I take R0 and I apply this automorphism, then I will see that that all sequences in the image will have this property that the only forbidden words between two hashes at the distance exactly 2k minus 1 is the word which consists of ak minus 1, k minus 1 repetitions of the symbol A, B, and then followed by the k minus 1 repetitions of the symbol A again. So the xk is a subshift xrk. So xk is the image of phi k of x0, and it is the subshift xrk, where rk is this is the new set of forbidden words, and it has the following forbidden words. And instead of this word, instead of 2k minus 1 word, we put here, and then we follow with the same words. So what it means is that the language of xk differs differs from the language of x0 only when we look at the words of length 2k plus 1. So if k grows, then those two languages are the same up to a longer and longer words, and therefore we see this. And of course, each phi is an automorphism, so it gives us a conjugacy between x0 and xk, which means that x0 is really a condensed point of my uh, uh, relation. So this ends the proof of this simple fact. The remaining proofs from that paper are of a similar flavor, just technically maybe a little bit more complicated than this simple procedure, but the main features they are the same here. Okay, so now to finish uh, some outlook. Of course, the question does not end on the subshifts. Uh, you can ask the following question: uh, how it looks for other interesting dynamical systems. So, say for there's a question about topological conjugacy among uh, all homeomorphisms of the Cantor set, or about the topological conjugacy of all minimal homeomorphism of the Cantor set. So here we also have some results, but this requires there is the same. We compare the complexity of those equivalence relations in exactly the same way using Borel reductions, but our relations they do not no longer have countable equivalence classes. So this this opens a possibility that maybe they are no longer Borel. And this is in fact the case. Neither the topological conjugacy relation for homeomorphisms of the Cantor set, nor the topological conjugacy relation on the subspace of all minimal homeomorphisms of the Cantor set is a Borel equivalence relation. It is so-called complete analytic equivalence relation. So still you can say something meaningful about that, but this requires an extension of our vocabulary, and this is maybe a story for another 90 minutes lecture. So I think I will stop here. Matt Foreman produced a nice, a very nice survey article when you can find more information about that, about possible problems in dynamics, because it is worth mentioning that I was concentrating on the topological aspects of this theory, but you can also ask meaningful questions about measure isomorphism between automorphisms, preserving the Lebesgue measure, or about even the measure conjugacy measure theoretic isomorphism between diffeomorphism of compact manifolds. And here it is worth mentioning that there are a lot of results done by first Foreman, Rudolf Weiss, then Foreman and Weiss, and recently by Maglies Gabriel and Philip Kunde, and others, Bob Peng, Benjamin Weiner. So those are all names worth checking And yeah, this is what I presented is a kind of a very special, um, well, a special case of a very active field of research, which is yeah, full of many open problems. So okay, I think I will stop here. So thank you very much for your attention.
Thank you. Thank you.
Hello, hello. I can't hear you.
Can you hear me now?
Yes.
Okay. So are there any questions from the audience? Can bring the microphone to you so Dominik can hear us. Maybe I can start with a question. So you mentioned this open problem that's whether every amenable CBER is hyperfinite. Is there any counterexample to this?
No, I don't know. I don't know any example of an amenable relation which would be for which the answer is not known. I'm pretty sure that specialists know better than me, but I'm sorry, I cannot. I don't know any.
Thank you. Thank you for the answer. Are there other questions from the audience? If not, then I would like to extend a warm thank you from the participants and the organizers for your very, very interesting mini lecture, mini lecture series, and also another applause maybe from the audience.
Thank you very much.
Thank you. And then I have a couple of announcements from the organizers, but I will stop the recording first. So make the announcement.
Only for the participants on site, so I don't think I need the microphone for that. Tomorrow after lunch, there will be a bus to Poznań train station starting at 2.